All right, so I kind of got cut off on the last one. As I was saying, of course, the moon is orbiting the Earth. 9 o'clock in the morning, you go out and you notice, let's say you're at the shore and you notice that it's high tide. It's exactly high tide at 9 o'clock in the morning. The next morning, you go out and see the moon has moved, and it's moved by about 50 minutes. And so 50 minutes later, so it wouldn't be 9 o'clock anymore. The next day it would be 9:50. So 9:50, because the moon would be right here, the high tide has shifted, and of course the low tide is shifted by 50 minutes. This high tide is shifted by, and so forth, right? It's not exactly the same, right? Because it takes time it takes hours, for the moon to get over, you know, move each time. The moon is still moving, right? And so these things are not static; they're constantly moving around the Earth. Uh, you know, in roughly 50 minutes per day, they shift. All right, so you might have noticed that you go to the beach and it's high tide early in the morning, and then as if you're there for a whole week, it won't be high tide in that same time in the morning again. All right, so that's the basic idea. This is the hardest one to explain, and that just has to do with the inertia of the water. That is, the water piles up, the same as if you're spinning a bucket over your head really fast, or not really fast, but fast enough that the water doesn't come out. That's the basic idea here. All right. So this is the difference between high tides and low tides. You can really see in some locations on the Earth, you can really see the difference. Where this is, let's say, this house right here, and then notice there's no water anywhere, and then there's huge amounts of water. It tends to be the higher you are in latitude, or towards the South Pole, it'd be the higher you are or the lower you are in latitude. It seems to be greater, towards the northern latitudes or the southern latitudes. Let's see. All right. Now this. So we just talked about the moon contributing to the tides, but there are actually, since I know that we mentioned before that the sun is much further away than the moon, but since the sun is so much more massive, it still contributes to the tides, right? And so here's how it does it. When the moon and the sun are either 180 degrees apart, that they line up, or they're on the same side as the Earth, right? So from the Earth's perspective, the moon is on the opposite side of where the sun is. Of course, that's a full moon, and when the moon is over here, that's a new moon. All right, so when that happens, you get what are called spring tides. So these are, let me make sure I get this straight, okay? Because sometimes I confuse myself with it. So these are the highest high tides that you can possibly have, right? So I always like to think of like a pylon in the ocean, a pylon that's holding up a pier in the ocean, right? Or by the side of the ocean. And so if you were to look at that pylon and mark like the highest high tide during the year, or during over the course of a year, that'd be a good way to say it. There are certain high tides when the high tide occurs when there's a full moon or a new moon, and those I guess they were first noticed in the spring because they don't have anything to do with the spring. Okay. But they're named the spring tides. Okay. Everyone understand that it's nothing to do with the spring, nothing to do with the time of the year or anything like that. It just has to do with the phase of the moon, right? The phase of the moon is either a new moon new moon is on this side. New moon, right, when the moon is on the same side as the sun, or a full moon. That's when you have a high tide. When those two phases occur, you're going to have a higher than normal. Well, I don't know. It's hard to say what's normal, right? You would have the highest high tide and the lowest low tide. All right, so during one of these spring tides. All right, so when the moon's over here or over here, you're get. Oh, well, I'm sorry. So this is the highest high tides and the lowest low tides. All right. So now we switch to. Sorry, I didn't mean to jump to when the moon is. All right. So now if we jump over here, when the moon and the Earth and the Sun are at 90 degrees to each other. So this one was when the moon, the Earth, and the Sun were either at 0 degrees or 180 degrees from each other. Now the moon, the Earth, and the Sun are going to be at 90 degrees. And of course, remember the phase of the moon is either a so that's the first quarter moon or the last quarter moon, also known as the third quarter moon. Right. So when it's the first quarter or the last quarter moon, those are called neap tides. All right. So that in that particular case, so you're getting. Let me make sure I say this right. During a neap tide, it would be the lowest high tide that you're going to get, right? Because the sun is actually working against you, right? In this situation for the spring tides, the sun is enhancing the high tides. So it's the highest high tides and the lowest low tides. All right, so, yeah. And then for this one, it is the lowest high tides. And let me think about it. Hold on. Let's see. Did I say that right? This is the low. Yeah, I always get myself confused about these. So this would be the lowest high tide, right? Because the sun is working against you, and the lowest high tide and the highest low tide. Yeah, that makes sense. All right. So those are the spring tides, and when the moon is in these phases, the first quarter or the last quarter, those are called neap tides. All right. So and this is the last little thing that we're going to have about the moon, or with the moon. I think we're just about done. And so this last thing is what's called tidal breaking. Okay, so this is what I kind of mentioned a little bit about this in earlier videos. All right, so the idea here is, because the moon is so close to the Earth, the moon is acting on the Earth, at different strengths at different points on the Earth, right? If it was further away, it would just act like a point object. What I mean by that, it wouldn't act like some object that's extended into space, right? All right. Anyhow, because of that, right? There's a small there's a small torque that is applied to the Earth from the moon, and the moon on the Earth. From the moon to the torque on the torque on the Earth due to the moon, and the torque on the moon due to the Earth. All right. And so that's what's called, that's this idea of tidal breaking. And so the result of this is that, the Earth is slowing down its rotation. And the other thing that's happening is that the moon's orbit is getting slowly, very slowly, right? Very, very slowly. It's getting further and further away from the Earth. Right? So that's, this all has to do with what's called the conservation of angular momentum. I'll briefly go over that because it's something that we're going to encounter again when we talk about the rotation of other planets. But the conservation of angular momentum is it's actually a fairly simple idea. So when something is spinning, okay. Now to get something spinning or to slow something's spinning rate down requires what's called torque. All right. So when there's no torque that's applied, then what happens is angular momentum is conserved. I mean, it's a basic idea of physics, is that angular momentum, just like energy, is conserved. That is, there's some quantity which happens to be called angular momentum that is the same before as it is after. Okay, so here's a concrete example of the conservation of angular momentum. If you had, like, let's say you had an ice skater spinning around, on their skates, and what they do is, let's say they hold their arms out, right, really as far away from their body as possible. So they hold them straight out. They hold their arms straight out, and so they're just spinning in one location on the ice. And so if you think about what happens when they pull their arms in towards their center of rotation, when they pull their arms in, they begin to spin faster. And so that's the idea of the conservation of angular momentum, right? Is the mass of this ice skater has been redistributed, and therefore the spin rate is it's either got to increase or decrease, right? And so this tidal breaking, which is of course caused by the moon's synchronous rotation, that it's also causing the Earth to slow down. I mean, it's not slowing down a lot. Okay, let me think about what it is. I think I don't remember the number. I should look that up actually. So in the back of my mind, and I'll look it up to make just, if I'm wrong about this, I'll state it shortly. So in the back of my mind, it's something like 3 milliseconds per century, right? So now think about that, what that is, right? 3 milliseconds. Okay, so that would be 0.003, and that's if I'm getting the number right. But it's something in the milliseconds. So I think it's 0.003 seconds. So the Earth is slowing down by 0.003 seconds more each century. So the length of the day, there was a time when the moon was much, much closer to the Earth. And when that was going on, the Earth spun around a lot faster. And so if we use this idea of angular momentum, and get the moon as close to the Earth as possible, it turns out that there was a time billions and billions of years ago, more than 4 billion years ago, where the Earth was actually spinning around once every 5 hours, right? So that's just with the angular momentum considerations, right? If you have a body that's rotating around the Earth, and you can figure that out, right? can figure out how fast